Right. So moving on to the final speaker of this morning's session, Dr. Nick Walton. I only learned this morning that Nick was actually part of STFC for 10 years, managing the Isaac Newton group of telescopes in La Palma. He's been a member of the Gaia science team since 2007, is now the Director of Research at the Institute of Astronomy at Cambridge. So over to you, Nick.
Difficult to follow that one, but perhaps from the space science point of view, just to point out that we're doing some pretty good work here, and I think equally interesting, and it does have links to the manned or human exploration program. Let me see. So I'm going to talk about Gaia. So Gaia has been observing the sky continuously for getting on, well, since 2013. It was its launch. Basically, it's mapping the Milky Way, effectively. That's it in a nutshell, giving us precise distances and astrophysical characterization of a large sample of the stellar content in our Milky Way. Plus, it does a lot of other things. It looks at solar system objects. It looks at exoplanets. It looks at quasars, the distant cosmos as well. In a nutshell, it's basically a very large camera in space. A large chunk of this actually was made in Chelmsford, the detectors, and a lot of the avionics. A significant part of Gaia was constructed in Stevenage, so a sort of east of England bit there. I'll put a plug in for the east of England, if you like. We've got on board, so basically it's integrated system of detectors, a camera for measuring positions effectively, spectroscopy, low resolution spectroscopy. This enables us to characterize the objects that we're actually looking at, and the radial velocity spectrographs, a higher resolution, which gives us an idea on the radial velocities, and also gives us some more detailed chemistry. So Gaia had a 5-year nominal mission. It's recently been extended to end 2022. We'll probably get extension to 2025, when the cold gas propellant, as they call it, will run out, and it will stop its in-flight observations. And we're looking forward to a final Gaia data release in 2030. So that looks like the same sort of time when we're going to see those people wandering around on the moon. So when they are up there, actually, just to give you an idea of how precise Gaia can measure distances and angles, it's all about measuring angles, actually, because it's measuring the sort of apparent motions of objects on the sky. Well, basically, we've got precisions at a few micro-arc seconds. Now, if you can imagine standing on the moon, which obviously David doing more than imagining, then they would be able to resolve a euro coin. So I probably should replace that with a 10p or so. This gives you basically the ability to measure distances of objects out to the outer reaches of our Milky Way with very small errors, and also it's a direct measurement. There's no real modelling involved here. This is a direct measurement of observations, and once you've got the distances of objects, you can then start to determine their absolute properties, so absolute fluxes and so forth. Right. So looking at the sky, you don't normally see this when you're doing your amateur photography of the night sky, but when you're at the micro-arc second precision levels, you can track objects, and the spiraling motion is the parallax, which is really reflecting, giving us the ability to measure the object's distance, and this is really related to us going around the sun and observing it a couple of times with a big baseline between our observation points. And then we can also see the object's motion, the proper motion, so-called. So to Gaia, basically, this night sky is in motion. Gaia has been putting out data releases for a little while now. We had our first release in September 2016, which is a sort of taster release. It came out almost, well, actually, that was purely by luck, actually. The 1,000 days since launch, we realised that a few days before, I think, the release, so we managed to get the graphics sorted out. And that really gave us positional measurements. We had a big release in April 2018, which gave us increased the catalogue and brought out the colour photometry. We had a large release December 2020. COVID may have been hitting us full on at that period, but we kept going and got our data releases out. This was releasing a catalogue of about 1.8 billion sources, and data release 3, June 2022. We had a very nice release day, hosted in fact by the RAS down at Goonhilly. It was very nice to see the space ecosystem down in Cornwall there. But this is the release where we were able to put out the catalogues with the astrophysical characterization of many of these sources. And basically, we have large samples, positions, distances, colours. We can determine what those objects are. We can pull out binary star systems. We can pull out exoplanets. We can pull out solar system, asteroids, and so forth. So these are the sort of releases, and the data keeps coming. We're observing now, actually, Gaia's ticking away up there, and we're handling the data that's coming down and preparing for the next data release, which will be in a few years' time from now. Gaia's a collaborative process. There are many engineers and scientists working on the analysis of the data, pushing out the data products, and they are located around Europe. The UK is significantly involved in the Gaia processing, and I guess I better say thanks to the Space Agency for supporting this. And we have the analysis going on there. I should mention some of the numbers, actually. We reached 4th of July, that's a nice day to reach 2 trillion observations. So these are astrometric measurements. So this is a very a big data processing project. And I've just put up some faces, actually. We sometimes forget there's a lot going on behind the scenes, and these are some of the people that are actually responsible for pushing out the Gaia data. And there's a whole range of, it's nice, from all over Europe. It's very much a European effort, and there's a lot of diversity and a lot of inspiration, inspiring people involved in pushing out these data products. And we're working towards the next data releases in 2025 and 2030. Right, this is some of the data getting access. The little clicks are when we put out a release, and you'll see the hits to the archive, and there are nice big peaks when the data comes out, but you'll notice that each time there's a data release, the plateau goes up. And this reflects really that every release is more richer and wider data sets, and here's the explosion of people pulling those data. So what is Gaia? So that's a little bit about the sort of behind it. What does it actually produce? What do we see? So this is a map that was released in 2016, and here you see this was based on the first year of observations. And you can see the imprint of the observational characteristics of the actual scanning law, the way that Gaia scans the sky. It's spinning at 1 arc minute per second. It's got these little microthrusters that can do that. I've already got the 5-minute warning. I've got my clock here, so I do know I'm not going to be done. Right. This is the first release, and you can see the imprint. And those structures there. Do we get a thing here? No, that there's a little green thing up there which spoils some of the pictures. Anyway, those go away once we get more data, and you'll see that as we go up. Here we've annotated some of the objects. So basically, you can see towards the galactic centre. You can see the dust planes. Any little dot really down by the SMC 47 Tucana, for instance. They're little globular clusters, concentrations of stars. You can see even some nearby galaxies, Andromeda. You're going to see about Stephan's quintet. That's sort of a bit to the right of Andromeda there in this coordinate system. This is the source counts, and you see nicely the large magnetic clouds there. As we go through to the DR2 release, we've got more data, more months of data, 22 months, more or less doubling the data set. Some of that, those artifacts have gone. This is the color, because we put out the red and the blue color information. This is 1.3 billion objects. Here we go with EDR3. So this is even more data, 34 months. We're really starting to see, you can really see the nice structure in the Magellanic Clouds. Each one of those, these are just basically summing up the sources in the particular resolution elements in this map. What I'm going to show you here is how this is, I'm sure that Gillian this evening or this afternoon is going to talk about Stephan's quintet. This is the release data, beautiful data coming out from the Webb telescope at the moment. But how does this sit in terms of Gaia, and how would this fit? And this is sort of give you an idea of sort of field of view. So at the top we've got we're centered on Stephan's quintet. You can see the color map from Gaia, from the DR3 release, and at the bottom it's the field, and I've just put in there the NearCam mirroring image of Stephan's quintet that went into that. And now if we move this thing along a bit, you'll see we're going to start zooming in, and you can see the scales, and we sort of start to see all of these objects. So we're getting down to the fuller resolution in Gaia, and these are basically sources. All the dots are actually stars, and here you can start to see the field coming in, and the scale bar. We went from the whole sky, 40,000 square degrees, and now we're going down to a few arc minutes. And basically, Gaia is giving you the framework. Each one of these objects, we know what those objects are. We know the type of star it is. We know its position, and you can see that when we put out the catalogues, the little red things that are going to come up in a second are the Gaia sources in that field. And Gaia does detect, of course, each one of the major galaxies in that group, and all of the little red things. You can basically get a full set of astrophysical parameterization. So you get masses, temperatures, you get specific gravities, you get the chemistry, you get the whole velocity properties. And these are the sort of things that you can do. Radial velocity maps. These are made up of hundreds. That's sort of 50 odd million objects. The mapping the interstellar dust through the Milky Way, the chemistry of the objects. You can see the rotation signatures of us around the centre of the galaxy. There was some nice work went out about that. In terms of science, we've got a massive amount of science coming out of Gaia. It is now the most scientifically productive mission of ESA, basically. I think, and now we're putting out about 5 papers a day. People are very busy with this. The annual rate is getting off 2,000 papers a year now. HST Hubble is about 1,000, so this is very nice, and it really covers the real cross gamut of science, which is really spectacular, from asteroids, exoplanets, all the way to fundamental physics. Got to keep my eye on this now. Right, Milky Way. So one of its big things was, how does the Milky Way form? How do we get to that sort of structure? How do we build this up? And if we think we want to look back in time, and we want to compare what we see, if you like, and we want to sort of put the puzzle together and see if we've got observational evidence for one of the main technique, or one of the main theories, hierarchical theory of galaxy evolution, basically accumulation of smaller galaxies, nuclei forming from dark matter clouds and so forth, and looking at the various parts of the galaxy to see, what this can tell us. So this is sort of nice simulations. ESA are very good at putting out these the graphics, which is great. So now we're going to say with Gaia, what are we doing here? Let me see if I can get that graphic going. So we're looking at stars. That's 50,000 stars there. How do you know what they are, if you like? So now we're going to do the sorting. If you've got their parallaxes, gives you the distance, means you can actually put absolute parameters on. So that's on the left, you've got absolute luminosity, absolute magnitude in that case. Basically, hot things that are blue are basically the top left, and big hot things that are red are on the top right. And now we can sort of sort our objects, if you like, in colour space and brightness space. So this is what we do to form these so-called Hertzsprung-Russell diagrams. And when you've got really high precision, i.e. the errors are not all over the place, you can actually start to look at different populations. Bottom left, for instance, white dwarfs. You can look at different sequences. You can look at how the atmospheres of those white dwarfs are, and that tells you things about planet formation even. For all of these, with Gaia, you can pull out the spectra. So it tells you M's sort of low mass red stars, hot A stars. Looking at the solar system, there's about 180,000 asteroids. This is the total set. The sun's in the middle, the yellow dot. The Earth is sort of not to scale, of course, and you can see that's the release on Gaia. Release date 13th of June. You can see the Trojans, and you can see the orbital parameters of these things. you want to pay attention to the ones which sort of go way out and come way in and cross the Earth orbit there. These are the ones that we're sort of worried about. I'm getting to the end. So that's from the sort of nearby side of things. Going a bit more esoteric, picking out one object out of that 1.8 billion. How do you know what something is? This is fun, something with a strange astrometric binary signature, and actually it turns out to be a solar type star around a period of sort of 100 days or so, going around what must be a black hole, and it's dormant black hole, and this is a unique object, a real puzzle for the theorists. We're going to get more. Most of these are not discovered like this, and here you can only find these through astrometry. And this one is really the building blocks of the Milky Way, and these are really recent results, and there's teams in Cambridge in Europe and colleagues from across the States. Basically here, quickly showing that from the proper motions, the Gaia chemistry data, we can pull out samples of objects, metal-rich objects on the left, top left, next door, the metal-poor objects, and we see the metal-poor objects are concentrated towards the galactic center, and these are now thought to be the evidence of the really early stages of our proto-galaxy. So what started off the formation of the Milky Way, so there's about 20,000 stars in that metal-poor population. And we also find over the sky these huge sort of streams, which are the later evidence for accreting. The Milky Way is very good at gobbling up nearby galaxies. So we are an accumulator, which is a nice place to be, I suppose. And there's one of our latest ones, gobbling up the so-called Gaia Enceladus, and that's enabling to form the Fictis, Spictus and the Findus. Very nice, sort of showing that Gaia is basically truly revealing the formation history of the Milky Way. My last little plug is we have plans for the future. Gaia near. Let's look where the real stars are. Gaia works in the optical. You saw all the dust clouds. Not very good if you want to look at stars behind the dust clouds. Go into the infrared. We have some really superb technology providers in the UK who can provide the detectors that will work in the right sort of mode. Bit of a detail here, but I hope the right people are nodding here. And we want to push this along because it gives a really nice chance for the UK to take a leading role in what could be an L-class mission. And we hope the space science budget recovers a bit to enable this sort of thing to happen, so that we can inspire space scientists across the board in the 2040s. And that basically was it.
Well, I think there's only one word to describe that talk, and that is wow. I mean, really, it's absolutely phenomenal. And I love the way that you link in with all the previous talks. You know, you've got there your team sports, and all of the faces you showed on there shows how broad the team is. So that was phenomenal. And just the superlatives, 5 publications a day coming out of the Gaia
and they're refereed.
And their referee. It's absolutely phenomenal. And it's great linking to the exploration, whereas Dave's team exploring the moon and Mars, you're exploring the furthest reaches of the entire galaxy. So you're a true explorer. There must be a question from the floor over there, please, Chris.
Nick, thanks very much. It's hard to get across to non-astronomers how important the Gaia mission actually is for the whole of astronomy. And it's great that ESA are funding the mission itself, but as you've indicated, the value of Gaia is really around the analysis of the data. And the analysis of the data is funded by national funding. It's not funded through ESA. And challenge that national agencies often have is balancing the continuous operation of a successful mission that goes on for several years versus the need to build new instruments for future missions, and there's always a tension. Do you think we've got the balance right in the UK now between keeping alive the mission data streams that are of successful missions like Gaia versus the continuous pressure to try and fund the next generation?
This is what you call the incoming question. So I will say probably.
Excellent.
And move quickly on to the next one.
Richard, final question, I'm afraid.
And I should say, after this, I've got to go off to a review meeting where I'm defending a grant for exactly that, but from STFC, not the Space Agency. So I'll give a longer answer to them.
Okay. What I should ask you really is, where are you on there? I can't actually find you yet, but never mind. The real question is,
there I am. Yes, I can see me.
okay. You have an incredible data set. No question about that. Obviously, the focus is on the sky map of the Milky Way, but that is brilliant. But your images obviously show the large and small Magellanic clouds, Andromeda, and so on. And you touched on this a little bit, but how good a job can you do on the objects like that? By comparison,
for the local group, we can do a reasonable job. We can't really do the astrometry, but we can do the proper motions, and we can see the rotation of M31, for instance. There's some beautiful work going on. I've got the wrong pictures up. For the Magellanic Clouds, you can see the bridges between the LMC and the SMC, the smaller and the large. You can also see the populations, how the Milky Way is stripping the Magellanic Clouds itself, and we can pull out those populations. We can do a very good job on those populations. One of the plugs of Gaia actually, we do an even better job, because not only do we do the obscure regions, but we've also enhanced the reach out for sort of outer regions of the halo, which unfortunately a lot of exciting stuff is going on in the sort of 50 kiloparsecs further, 50 to 100 kiloparsecs regime. But yes, I only pulled out a couple of sort of topics really.
it's very impressive.
Thank you very much. I'm afraid we're going to have to move on to the coffee break now, but a round of applause once again for Thank you.